Thanks for attending that last talk of the conference by Ofer Zeitouni. So before we start, I wanted to thank again the co-organizers, so Codina Kotar and Tyler Helmut, and so all the co-organizers, including me, would like to thank the Newton Institute for their great support, and thank all of you for your participation to the conference. So Ofer Zeitouni, so we are very honored to have Ofer close the conference, and his talk will be about partition function asymptotic for 2D random polymers in the subcritical regime.
Thank you, and maybe a round of applause for the organizers. It has been a very nice week, at least for me. Okay, so I'm going to talk about directed polymers, so that without further ado, let me state a general, very quickly we will specialize the model, but let me first start with some generalities. So suppose I have an infinite graph, and on each I have IID weights, and what is important here is that they are a function of time, which is here indexed by I, and the location on the graph. So those are IID. Throughout the talk, these guys are going to be standard normal. So many of the things I'm going to tell you about have analogs and generalizations to non-Gaussian, but I'm going to stick to that. And then the other player in the game is a random walk on chip with law PV, which I didn't write here nearest neighbor, although that will be the focus very soon. And we have a parameter, beta, which is an inverse temperature. And then we change the law of the random walk by a weight which is proportional to the total sum accumulated along the trajectory. Okay, so in this case, this is the sum accumulated along the trajectory. SI is our random walk. This is a normalization factor. Of course, since I divide by Zn, I could write or not write it, but it makes sense to write it like that. And the partition function is this object. Okay, so this is the weight that is needed in order to make that into a probability measure. So now we have a law on the random walk. And a crucial observation is that this guy here is a martingale. Now, this guy here is a function of the environment. It's not a function of the random walk anymore because I took expectation on the random walk. So it's a function of the environment. And as function of the environment, it's very easy to check that it's a positive martingale. And therefore, it has a limit almost surely. This is very, very general. It's true on essentially arbitrary graphs without too many conditions. Now, under very mild conditions, you can show that. So the main question is whether this limit is 0 or not. It's a positive martingale, it converges, but it might converge to 0, in which case things will maybe not be so interesting. So under very mild conditions, which are satisfied in particular on ZD, this event has probability 0, 1. So either you converge to 0 almost surely or to a non-degenerate random variable. And there is a monotonicity in general such that you are positive almost surely up to that point, and you are equal to 0 above that point, so that's a critical temperature there. And there are names. So this region is called the weak disorder. So the region in which the partition function does not degenerate is called the weak disorder. And the other one is the strong disorder. And there is another parameter. Okay, maybe before this other parameter, let me say that there are some, in quite general situation, there are other descriptions of weak and strong disorder in terms of localization of the path. Okay, where in the strong disorder, as you can imagine, to some extent the path follows some points in the environment which have particularly large omega. Now there's another important parameter, which is if the second moment is finite of Zn, then Zn is uniformly integrable. Okay, and by finite I mean it's uniformly bounded. Then Zn is uniformly integrable, and then Z infinity is positive almost surely. And we set beta 2 to be that region where this condition holds. Of course, it's part of the Wicked disorder regime. Very good. Now, I chose to talk about general graphs just to make you aware of some surprises. So one of them is, to me, it was a bit of a surprise, but beta C is not monotone in the number of edges in your graph. So if you take a simple walk, you can create graphs where adding edges does not increase beta C. And there are graphs where beta 2 is 0. In fact, for percolation cluster, you can show that in dimension 2, beta 2 is 0, and in reality, beta C is 0, and it's 0 in any dimension, which again was a big surprise to me, because in 2 dimensions, random walk, there's a Brownian motion scaling limit, but still, in terms of weak and strong disorder, these graphs, the percolation cluster behaves very differently than the full graph. Okay, so as promised, I'm going to specialize to the case of ZD now. And in that case, this goes back to the physics literature essentially from the mid-80s. And on the mass side, the foundation works are work of Imbri and Spencer in '88 and of Bolthausen in '89. The latter work was particularly important because it introduced to this game martingale techniques. And this weak and strong disorder phase transition and the link to localization and delocalization transition was made in several papers, and in particular comets played a very important role in this game, and in particular for those who are new to, who have never seen this, there are lecture notes of his course in Saint-Flour, which are excellent introduction to the topic. But among other things, what these people showed is that in dimensions 1 and 2, there is no weak disorder. And in dimension greater or equal to 3, there is weak disorder. Hence, well, just as a comment, you would be able to think that making the process more transient by adding edges would help you to create monotonicity in beta C, but that is not. Okay, and in fact, very recently, it has been proved that in the strong disordered phase, the convergence to 0 is actually very fast. It's exponential. This is called a very strong disorder regime. So this was conjectured for a long time, proved only very recently. And again, this transition is related to localization, delocalization. I don't want to talk at all about that, but that's generalization. Okay. And maybe in the context of this conference, I want to point out that there is a link with the stochastic heat equation and with KPZ, and the link goes as follows. So if you take the stochastic heat equation, which is the solution of that. So by heat equation, I mean the multiplicative noise, the stochastic heat equation. And of course, this psi epsilon is a mollified version of white noise. So this is kind of the mollification thing. Then you can write a Feynman-Katz formula, and you will get the continuous time analog of the formula I wrote you before. Namely, I thought I had written it, never mind. You can also, of course, take the log of this equation, and that will bring you to the KPZ, to the same type of thing with the KPZ. And in that setup, there is similarly a weak disorder phase transition in dimensions 3 and larger. There are many homogenization results, convergence to a Gaussian equation, so to the additive stochastic heat equation for this situation. So I've listed here some of the names, Magnen and Unterberger. I had some series of work with Rijik. Those works were all in the regime of small beta, and then later Kosko, Nakajima, and Nakashima showed that this kind of homogenization results, convergence to Gaussian, holds all the way to beta 2, which is a natural limit for Gaussian. Okay, now, this talk is going to focus on the weak disorder regime in 2 dimensions. If you paid attention, you should say, but wait, can you go back to 2 slides ago? And 2 slides ago, we said there is no weak disorder in 2 dimensions. So how can I focus on the weak disorder in 2 dimensions? So the answer is, of course, you have to modify the model. And modifying the model, so this is a certain normalization. This is just a green function of 2-dimensional random walk. And what you could do is rescale your temperature in such a way as to get a meaningful limit. And it turns out that the correct rescaling is this particular rescaling by square root of log n. And now the partition function is a function like that where we multiply by this beta n. So is a model clear? So it takes the same directed polymer measure, and I'm looking at the partition function, but my temperature goes to 0 in a logarithmic rate. Okay? Good. But there's a problem now. Essentially, you have to restart the whole theory because this is not a martingale anymore. So even the convergence result is not obvious. This is not a martingale because a crucial point of the martingale was that the beta was constant. So when you went from n to n plus 1, the whole history didn't change. The part associated to the history, you could pull it out of the expectation. But now you cannot really do that. And okay, so if you now write Zn as Zn of 0, there's a very important series of papers by Caravena, San, and Ziguras, and many of the results I'm going to state now are due to them. So here is a first theorem. There is a phase transition with this parameter beta hat. So I emphasize what is beta hat. And in fact, you have a kind of Gaussian convergence. The log of Zn converges to a Gaussian random variable with a mean minus lambda square over 2 and a variance lambda square. And this lambda square is just this quantity. Okay? Another way of saying it, remember that Zn has expectation 1 by construction. So you could think of Zn as the exponential of a Gaussian minus whatever is needed to make the expectation 1. Okay? That's exactly what this is written in long form. So that's very nice. So Zn point-wise looks like a Gaussian random variable with this particular variance. And one thing to note is that this particular variance is, you can write it also as in an integral form. This will play a role in what will come towards the end of the talk. Okay, and in fact, a few years later, Lekonis and Ziguras proved that not only you have this convergence in distribution, but in fact all moments converge. So it's a stronger notion of convergence than just convergence in distribution. Good. So, I should say that this also extends to certain continuous models like the stochastic heat equation, etc. And recently there have been very careful, detailed expansion and new phenomena happening when you take beta hat to be 1 plus a lower order term. But I'm not going to get into that at all in this talk. Okay, so what is the starting point today? The starting point today is another observation of CSZ, which is the following. If you take the log of Zn, which we said converges to a Gaussian, and you subtract the expectation, so now you really have a Gaussian, a centered Gaussian random variable in the limit, but now you blow it up, and you blow it up by square root of Rn. So now you get yourself a field that pointwise blows up, okay? And if you see me talking about it, and you know a little bit about what I've been interested in recent years, that's kind of an interesting object because maybe it converges to some Gaussian free field or something like that. And in fact, that's what they proved. So what they proved is that this Gn converges in distribution to a certain logarithmically correlated field with effective variance given by this factor. Okay? And they wrote the correlation function. So so now I should say something about the meaning of this integration, of this convergence, because it plays an important role. So this convergence just means that if you integrate Gn, now thought as a point on the, x is now a point on the unit square. So take a nice smooth test function on the continuous unit square and integrate this piecewise constant Gn with respect to that continuous function. Then you'll get a Gaussian variable whose variance you can compute from the logarithmic correlation on the right-hand side, which is finite. What I want to emphasize about that is that this essentially looks at the large scale of this field. Because this log correlation is really completely determined by the large scales of the field. Very good. And this G, okay, solution of Edward Wilkinson, which is the heat equation with additive noise, which is the same result that you get in dimension 3, but with beta constant. So this is a correct rescaling, and really in a very strong way, this is a good notion of weak disorder. Okay. There are, as I said, analogous results in continuous setups. There's a very nice paper of Gu from a few years ago, and of Nakajima and Nakashima, besides the work of CSZ. Okay. So now I repeat this thing. Now, I am interested in extremes. You got yourself a Gaussian field, which blows up pointwise. So you can ask, what are the extremes of this Gaussian field? How big does this Gaussian field look like when you look over the unit square? And the first step, if you ever try to look at extremes, the first step to do before you try to understand the structure of correlation, etc., is to understand the pointwise tails. Just one point, we want to understand the tails of one point. So this means computing, so what does that mean? Well, the pointwise tail, what tool do we have to understand the pointwise tail? Well, essentially Chebyshev inequality, what else? Computing exponential moment. So this motivates taking exponential moment, but if you look at it, what does it mean to take exponential moments? So taking exponential moments of this variable Gn here just means to take moments of Zn, but to a high power, which involves square root of Rn. So what you really want to do is exponential moments of Zn with Q, which is of this order. So Q's moment, but Q of this order. This is what you want to do. And we can now do that. So here is a theorem. Forget about the technical conditions, but note that they work for Q, which is of order of square root log n. The expectation of Zn to the power Q is bounded above by what you would get if it were Gaussian. Okay? So you get what you would like to. So not only is the field, but also high moments of the field, at least at the level of the upper bound, hold true. Good. So that's the first theorem. And I want to make a few amplifying comments on this. So first of all, if we look at fixed Q, so this means just moments just the moments of Zn, but to a fixed moment, then as soon as you have a uniform integrability result, which means that these moments are finite, and you have convergence, weak convergence, you know that the moments are going to converge also. And this is indeed the method that Liconis and Zygouras have used. Okay, yes, that sentence is important. I'm going to show you that we have matching lower bounds. So in fact, the result is that this is the correct exponential moment. And to give a spoiler, this is not good enough for reasons that I'll try to explain later. If you want to do extremes, it turns out, although we did not know that in the beginning, but it turns out that this is not good enough, and in fact it masks the true behavior. So this is a bit cryptic, but just to keep your attention, because this will come up later. The restriction I wrote there is annoying. So what do I mean by the restriction? The restriction is this condition, this technical condition. It comes from the technique of the proof. It's annoying because if you were to do Chebyshev in order to get an upper bound on the extreme, this would not be good enough. The constant constraint is not good enough. Luckily, two things happened. One is that it turns out that doing exponential moments like that is not going to give the maximum anyway, so maybe it's less problematic. And the second is that this restriction has recently been removed by Clement and Schutter following a nice blocking argument. So essentially a relatively cheap argument building on this result. Okay. Now, in anticipation of what is coming later, it turns out that we need moments not just of the sum from 0 to n, but in fact we need blocks. We need moments of blocks. And the same technique as the proof I've described is going to give you that these moments give the same result with this variance, 1 over 1 minus beta hat squared t. So this follows essentially from this work plus the extra work. Here is a promised lower bound. This is much easier, no conditions. So you get the same type of result for the lower bound. And so the remarks is, of course, this matches the upper bound. You have similar bounds for blocks. So by blocks, I mean when you don't look from time 0 up to time n, but rather you look at some intermediate time. both the upper bound and the lower bounds extend to products of non-overlapping z and k prime. So what I mean by that is that you can look, maybe I will write it. So z and k prime is the expectation of the exponential, and here you have the sum from j or n equal k up to k prime of omega of I si minus the normalization factors that I'm not going to write. And by non-overlapping, I mean essentially the following. If you have here k and k prime, and now here you have a k double prime and k triple prime, so that's hence a non-intersecting, and you need a little bit of a gap here, but not very large. Then the exponential moments, the high exponential moments, behave like products. So you get the same bound with the product of the terms you would get from this part and this part. Okay? So that's important to keep in mind. And in fact, the method gives, the method that I'm describing is going to give that. Okay. Forget about this comment for the moment. And let me tell you something about the structure of the proof. So I want first, because I want to have time to say something about the proofs, I start with that, and then I'll explain to you why you shouldn't pay attention. But not completely. Okay. So, let's think about the important case, which is when Q is of the order of square root log n. So the completely standard thing in this business is that computing exponential moments reduces to counting intersection for pairs of random walk. So this is an equality which comes just from averaging the disorder. You see, it's, the left side has two expectations. The left side here has two expectations. One expectation is with respect to the disorder, and then there are Q expectations with respect to random walk. Now Fubini it. So push the expectation on the random walk inside. And now it's a Gaussian expectation. You can write what you get, and what it turns out that you get is just the sum, the pairwise intersection local time of the walks. Okay? So everything goes from getting, maybe those are two missing here. So everything goes from computing something that involves both random walk and disorder to something that involves only random walks. The disorder has completely disappeared. Now, you can do some a priori bounds and use Krasminski lemma. I don't want to give details. You can, instead of starting at 1, you can start at some time which is very small compared to capital N. This is important because at time 0, everybody starts together. All these Q random walks start at the same location. And allowing you a little bit of room allows a particle to kind of spread out a little bit. So essentially now you have particles that spread out, that have spread out a little bit. So that's the first step. Now the next step is going as follows. Let's define a bad event. And a bad event is that 3 particles collide at the same time, or that 2 pairs of particles collide at the same time, or of course 4 particles collide at the same time, or more than 2 pairs, etc. Okay, so this will be for me a bad event. That one of these happen at any time n is going to be a bad event. Of course, in the beginning, the bad event happened because they all start from the same point. But I'm not going to look at that from the beginning. I'm going to look at that from this time s that in the first step I told you I can easily take. And what you can show is that the expectation on this backed event is little order of the main expectation. And therefore, we can forget about it when we compute bounds. Okay? So from now on, so this is essentially, this is one of the reasons why we had this crazy condition that, and you can improve on it, but as I write it here, this is proved by Holder, nothing more. This is just a Holder inequality, nothing. Holder and union bounds. Okay. Now comes the heart of the matter. So now that we know that intersections are only in pairs, we can look at successive times that you have pairs and order our particles and look at this expectation, write it as essentially expand the exponential. And you get an expression that involves transition probabilities of simple random walk between different intersection points. So this is what is written here in full glory. Never mind what it is really, but it's really, you track the location of the random walks between their intersection, you track who intersects with whom, and you just write the product, the probability. Very good. So this is a diagrammatic description of what is going on here. So you see, what happens, we want to count pair intersections. And we already know that we don't have to worry about triple intersection or two pairs at the same time. So this allows us to define blocks. What are these blocks? Suppose these two particles meet at this location. Then it's pretty likely they will continue to meet many times because we are in 2 dimensions, the walk is recurrent, so they may continue to meet for some time. But there will be a last time before some other two particles collide. Right? So the other two particles may be one of these two plus a fresh particle that comes, or it may be two particles that came out of thin air. Okay? So this gives us, this defines for us a sequence of times that we call A and B. Between A and B, we have a block of intersection. Between B and the next A, we have no intersection whatsoever. And then at A, some other two particles start to intersect. Okay? At this point, there is no restriction at all on the distances between A and B. But what do you expect? You expect that the distance between A and B, inside the block, is relatively long. And then they will go away to their merry, to somewhere, and then some new particles will come, and you expect these transitions to be relatively rare somehow. But, okay, it is what it is. And now you can write everything in terms of this block length. So this is a block length AI minus BI minus 1, so this one, and the V is like that, and you get an expression. And the important thing is that this expression U, this capital U that appears here, involves essentially this block. So you start together and you go over a block until you exit. And on that we have relatively good bounds because it involves only two particles. So we know how to compute this kind of things. Essentially it's a number of returns of 0 of a random walk bridge. You start at 0, you end at 0, and you ask how many times you visited 0 in between. So we have good estimates on that. The heart of the matter is to get control on this P, which is a maximum of the step probability. So where does that P come from? I don't want you to decipher the formula, but just see that what we have to have a particle starting from here, getting to here, while another particle that started somewhere back came and hit here. So it's again the same as the probabilities that a two-dimensional random walk comes to 0, comes back to 0 at a given time. Okay, so you write this expression. You can compute, as I said, the U, which is a main term involving pairwise intersection. You can bound it by random walk. And the only thing I want you to note is that you get a term like that in which here you have something that depends on both little n and capital N, and the relation is the log of little n and the log of capital N. Just to emphasize what this is, the little n appears in how many steps you had, the capital N appears in the factor beta n. So both of them appear in this formula, and now they are not necessarily tied together. Okay, and now you can do a simple-minded recursion using the fact that we know what P is. Maybe I don't want to give too many details, so you can, if you do this simple-minded recursion, you can write the whole thing as a recursion with coefficients that satisfy a recursion of this type. So everything here is now more or less explicit, but turns out not to be good enough, and the actual argument, which is maybe a little bit difficult to explain, and I don't want to, maybe the picture is okay, I thought I had put here the picture. Yes. So essentially, there's a big difference between what I would call short jumps, which means things of this type, and long jumps, which are things of this type. What is the difference? For short jumps, one of the particles was chosen already, because it's the endpoint of the previous intersection. So you have maybe a short distance here, potentially distance of length 1, but the number of choices for the other particle is small, so you gain in entropy. You lose in estimate, but you gain in entropy. Whereas for long jumps, meaning two particles that came from far away, you have entropy, because you have more choices. You have log n choices, essentially. But you have better estimate, because it's a lower time, so the probability to intersect is lower. So by carefully distinguishing between short jumps and long jumps and doing an induction, you can improve this very basic estimate. Okay, so that's the main idea. What about the lower bound? So one thing to, maybe before the lower bound, one thing to note is that throughout this upper bound, you realize that you could do it for any k and k prime. You can start anywhere, stop anywhere. It can be the same type of estimate, except that particles will start far away from each other. Okay. So the lower bound is based on the idea that you introduce buffers. So, okay, here is a proof in its full glory when it was first written on my blackboard a few years ago. But essentially, what is going on is an appropriate decoupling. So what is a decoupling? You partition time. So this is a partitioning of the time. And the time partitioning is this particular choice. I don't, okay, it took a little bit of trial and error to find the right notion. So those are intervals that increase, and they increase by a factor that is very small, okay? And essentially what you're going to do when you have these little intervals L1, L2, and another L2, so that's kind of the basic block, is you're going to close your eyes during this interval L1. Namely, you will have two particles, or whatever number of particles you have, and you are going to not take into account the intersection of particles during this time. which gives a lower bound because it's exponential of the total sum of intersections. If you discount certain intersection, you get a lower bound. And then you're going to reopen your eyes. So now the particles had time to diffuse. And in fact, it's almost as if they started at 0 because the total time up to this point from 0 is essentially the same as this length. And now you open your eyes, you count how, with these particles well diffused, how many intersect during this interval, but for technical reasons, it's convenient to split it in two. And then you repeat this procedure. So this is what I call introducing some buffer zone. And now that you have a large number of intervals, the number of intervals is essentially logarithmic. So now we begin to be in business. We have a logarithmic number of intervals. In each one of them, we know what is the expectation, because it's just the ones that we discussed earlier. And because of the buffer zone, you can prove that essentially the expectation becomes a product of the expectation. So you get a good decoupling from this buffer zone. So this is a single interval analysis. So a single pair gives something which has this nice factor in it. And then you have to count how many match. They started far away from each other, so they don't like to match. But it's essentially the number of matches you'll get is essentially Poissonian. And if you could prove that the number of matches is Poissonian, trust me, everything would work well. So at this point, if you want to prove that the number of matches is Poissonian, all you have to do is go to methods for proving Poisson convergence. In this case, the convenient method is this two-moment suffice of Aratia and company. So it's essentially Chen-Stein. So Chen-Stein is built on creating neighborhoods of dependence and checking that you don't have too many correlations between your events. So this works here. Once you know that, you know the expected number of, you know the moments, and then you get this expression. And this expression leads you back to what you wanted. And I want to emphasize here this integral that appear here, which is exactly the same integral that we saw for the total sum of the variance. Okay, so I know it's a little bit rushed, but I wanted to emphasize two things. First of all, the lower bound already had into it this notion that you have different contributions from different scales. And more important, if you paid attention, the contributions are not the same for every scale. So if you took dyadic scales, if you looked from n to the epsilon to n to the 2 epsilon, the contribution is going to be different than the contribution when you go from n to the 4 epsilon to n to the 5 epsilon. Just going to be a different contribution. And, okay, so for some time we were a little bit puzzled that the variance expressions that appear in the CSZ formula for the log correlated field and for the actual variance are not the same. And the answer to that is that the expression for the variance comes from contributions of all scales, whereas the log correlation structure comes from the macroscopic scale. And those don't have the same variance. They simply don't. Okay? So another way of saying it is that if you tried to take the log correlated structure, but now you took test functions that are not macroscopic, but rather are mesoscopic, you would get a difference correlation. Okay? This comes, among other things, from this computation, but that's more or less clear from the description I gave you. So if we now go back to the problem that I was discussing, the toy model is not the usual toy model you have for log correlated fields. So for this, let me go a little bit to the blackboard. So for log correlated field, a very good toy model that essentially captures all the results is the branching random walk model, in which, or the hierarchical model, in which on each edge you have a normal 0, 1 random variable. Then the depth here is little n, which is log, in this case, log 2 of capital N. And capital N is the number of vertices at this location. And if you're dealing with log correlated fields, then this has essentially a log correlated structure, except that distances are measured on the tree instead of Euclidean distances. But essentially, it's the same. And it's a fact for this kind of models that if I look here, if I have here a field phi v, and I look at the maximum of phi v, where v is in the nth generation, this is going to be like the leading order of that. So first of all, this is going to be like a constant times n. And this constant that is written here is the one that would be the same as if these variables were independent. So this constant is determined simply by taking capital N and multiplying by the probability that phi v, a particular one, is larger than c log n. And taking the c such that this is critical. Okay? That this does not go to infinity. And, okay, if you compute it here it will be square root of 2 log 2 times, not log n times n. This is what comes out from the computation. But the situation changes dramatically if the variance is not constant. And in fact, in our model, the situation is that you can write the z, you can telescope the log of z as ratios of partition functions over interval of different lengths. Now, let's imagine for a second that the expectation could be factored into expectations of products. Then what is really happening? What is this expectation? Well, this expectation essentially means you go up to a certain time, n to the power k over k. You have a Gibbs measure determined by the polymer up to that time. That Gibbs measure gives you a distribution on particles. And now, for these particles that came from that Gibbs measure, you restart the process and you ask yourself about the next interval. So if you knew that this Gibbs measure has a tendency to let the particles be far away from each other, this is essentially like starting from 0 without this Gibbs measure and looking at the next interval. And in fact, you can prove that this is a situation. So because we are with beta hat smaller than 1, the effect of this Gibbs measure is not to localize the walks. The walks are actually spread out. So there is not much difference between expectation according to the Gibbs measure and expectation according to just independent walks. And that's what happens. So the expectation of the product of these guys will factor into products of expectation, even at the level of exponential moments. And then you go back to this model and you ask yourself, what happens if you have here a variance which is not a constant variance? Before I continue there, let me tell you the result here. So there's work that started with work of Bouvier and Krukova. Which considered a slightly different model, and then there's work of Fang and myself, around, I don't know, 12 or 13, I'm not sure, which says the following. Suppose that I have the same branching random walk as I described before, and suppose that the variance of the increment, so this is t, and suppose that the variance of the increment at location at depth t, so sigma square of t, is some sigma of t over the whole interval. Suppose I have this situation, okay? So the variance of the increment at this location is like that. Well, this is a nice smooth function. And suppose that sigma t decreases. So suppose that this function that I'm talking about decreases. Then the maximum, the maximum of phi v divided by n converges, in fact, to the integral of sigma of s ds from 0 to 1, which is less, strictly less than the integral of sigma square of s ds to the power 1/2. This is just Holder. This would be the, if you only took into account the variance at the endpoint and did the computations that I told you before. So you would get that. Here you would get this integral. There's a constant here, which is the same as square root 2 log 2, but forget about that. So the maximum is smaller. Okay? And in order to really, so that's a theorem, but in fact, for aficionados of this topic, this maximum, so let's call it phi star n. So phi star n is a constant times n minus another constant times n to the 1/3 minus another constant times log n plus order of 1. Well, those you can describe this. This is joint work with Pascal Maillard from a few years back. So this model we understand perfectly in the case of non-constant profile of variance. And the message of this talk is that in fact the same happens here. So this is not yet on archive, but hopefully it will come soon. So the idea is that you decompose this W that I wrote into these ratios, use the Gibbs measure idea to show that they decouple. Once they decouple, we just need to understand a sum of these particles, and then you can plug in directly to the method used to analyze this kind of situation. So you have increments that have different variances, and the reason you get this kind of formula, just to give you a taste of it, the reason you get this kind of formula is because here, when you wrote the formula at the end point, what were you really comparing? You were comparing the cardinality at this level to the probability of going above a level. But you have this constraint all along the path. So if you think of the path of the trajectory here as phi t, okay, or phi of t over n, that's maybe better to think of it this way, then the constraint in the endpoint is just the integral of phi dot square from 0 to 1, 1/2, should be smaller than, well, a constant. And you want to maximize phi of 1 such that this is true. That's what comes out. This is a completely equivalent to the product of quantity versus probability. This comes from the probability, and this comes from the quantity. And the exponent of the probability should be smaller than the exponent of the quantity. So if you try to solve this variational problem, of course, the best thing to do is a straight line, and the straight line is going to give you the right constant. Here, it turns out that you have to do the same problem, but of this type. And the solution, sorry, of course, here you have sigma square. So for every t, this has to be satisfied. So you have a constraint along the whole way. This constraint reduces the maximum. And the solution for this problem is that phi dot is just sigma. Hence this form. Oh, it's just a constant, I think. This constant. So that's the reason it works here, and that's the reason it works here with this decoupling provided by this thing. So, okay. So I don't want to say anything more, and I think I'll finish here. Thank you.
So if we take the square root of log n moment power of the point-to-plane partition function.
Of the?
If you take the high power of the point-to-plane partition function, and you look at the random field generated by this, do you believe that this converges to GMC or to Gaussian multiplicity?
So, what does converge to a GMC mean? So first of all, as I tried to explain here, the correlation structure is different. So it's certainly not exactly the same as GMC built on a GFF. So even answering, so there is a natural correlation structure here. Do I believe it converges to the exponential of a Gaussian field with that correlation function? Yes. But it's not the exponential of a GFF. That's really the message I'm trying to hammer here. Because intermediate correlations are different from what they would be in the GFF. In the GFF is a scaling variance process. So the intermediate variances are the same as the long-range variances. Here it will not be. I'm not sure. I think it will show up as a different limit in law than for the GMC, but I don't want to commit to it. I'm not sure. We plan to look at it, but first to finish this.
So maybe I was wondering, so is it possible to give, 1 minute heuristics of why you get the 1/3?
Yes. 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 It is possible. I will try at least. So, what happens in the usual case? In the usual case, by usual I mean when you have a constant variance. So essentially, because of the same reasons that I told you here, there is a linear line which is a barrier, and you cannot go above that barrier. In reality, it's slightly bigger, it's like that, but think of it as linear line. So your process is looking like a Brownian motion doing this. And the fluctuations in the intermediate scale are square root n. Okay? Now, what happens when the variance decreases is that it becomes harder to catch up. because your variance in the future is smaller than your current variance. So you have a balance between two factors. One is you have an entropy factor, which comes from the fact that you want your Brownian motion, except for the constraint of large deviations, to reach this level. You want it to fluctuate as much as possible, otherwise you will pay in entropy. But on the other hand, if you let it fluctuate, it will go to distance square root n, and then it will be harder to go up, so you will pay in large deviations. When you factor these two factors together and you optimize, it's easy to write. You factor how much it costs you when you go down, you optimize these two factors together, and you see that the optimum is t to the 1. So that's what, so it's really entropy versus probability, the usual entropy versus probability.